This error is because of wrong path for MNIST dataset in MNIST Python code in TensorFlow. To solve, change your code to the following code. These files are created in building a perceptron. A perceptron is a single-layer neural network. The concepts covered in this chapter, such as the fully connected layer activation function, stochastic gradient descent, logits, one-hot encoding, softmax, and cross-entropy will be useful here. You will learn how to define these components of neural networks in TensorFlow and use the network to train the MNIST data. Defining placeholders for input data. A placeholder is a tensor where the data is passed. Placeholders aren't specific values but will receive input during computation. The input size of the perceptron, number of classes, batch size, and the total number of iterations of batches are first declared. X_input is the input where the images will be fed later. X_input is the input where the images will be fed later. Y_input is the placeholder where the one-shot labels or targets will be supplied as shown here. The none in the shape argument indicates that it can be of any size, as we have not yet defined the batch size. The second argument is the size of the tensor for x_input and the number of classes for y_input. Based on the type of placeholder, we have sent the data as floats. Next, we can define after shape equals sign. Defining the variables for a fully connected layer. Let's define a simple linear classifier, a perceptron, by explaining the variables such as weights and bias. The values of these variables will be learned during computation. These are also referred to as parameters. The weight variables are initialized with normal random distribution with a shape of input size and number of classes. The input size is 784 here, as the image is reshaped into a single vector. The number of classes is 10, which is equal to the number of digits in the dataset. The bias variable is also initialized with random normal distribution with a size equal to the number of classes. The weights and bias are defined as follows. The initialization of the variables can be zeros, but a random normal distribution gives a steady training. The inputs are then weighted and added with the bias to produce logits as shown next. The logits produced by the perceptron has to be compared against one hot labels y_input. As learned in Chapter 1, getting started, it is better to use softmax coupled with cross-entropy for comparing logits and one-hot labels. The TFNN softmax _cross_entropy with _logits API from TensorFlow does this for us. The loss can be computed by averaging the cross-entropies. Then the cross-entropy is fed through gradient descent optimization done by TFtrain gradient descent optimizer. The optimizer takes the loss and minimizes it with a learning rate of 0.5. The computation of softmax cross-entropy loss optimization is shown next. The softmax and cross entropies are computed together from the TFNN package, which has several other useful methods. The TF-train has several optimizers, and here we're using the vanilla gradient descent. You can visit TensorFlow API documentation to understand other optional parameters. Until now, the placeholders, variables, and operations are defined and yet to be populated with softmax cross entropy with logits is deprecated and will be removed in a future. Future major versions of TensorFlow will allow gradients to flow into the label's input on backprop by default. We add _v2 to previous command. Training the model. Now you have defined the model and training operation. The next step is to start training the model with the data. During training, the gradients are calculated and the weights are. The variables have not yet been initialized. Next, start the session and initialize the variables using a global variable initializer. The preceding 2 lines are required for most of the examples in this course. It is assumed that you will use these 2 lines wherever required. Now the graph is ready to be fed with data and start training. Over a loop, read the data in batches and train the model. Training the model is carried out by running the session with the required tensors. The optimizer has to be called in order for the graph to update the weight. The first argument of the run method can have an array for which the outputs of the values are. We pass loss because printing loss tells us whether the model is getting trained or not. The loss is expected to decrease as we are minimizing. The feed dict is a Python dictionary used to directly feed the input and target labels to the placeholder. Once this loop ends, the loss should be generally lower than 0.46. Next, we can evaluate how well the model worked by computing the accuracy, as shown here. The prediction should be the index of the maximum active. It should be compared with the ground truth on MNIST labels for correct predictions. The accuracy is calculated using the average of correct predictions. The accuracy of the data can be evaluated by running the session with test data as the feed dictionary. When the whole program is run, it should finally produce an accuracy of around 90%. The definition of the model may seem too explicit without simpler APIs for training and testing.